All right, let's dive right into this. Carbon monoxide. You already know it's odorless, colorless, and incredibly dangerous. But since it's this invisible byproduct of incomplete combustion, how do environmental regulators actually track it down out in the field? Well, today we are unpacking EPA Method 10. And as you're going to see, this is the official, highly rigorous procedure for becoming a literal ghost hunter of carbon monoxide in industrial emissions.
Because think about it, how exactly do you catch an invisible gas? When a power plant or an industrial stack is pumping out emissions, we can't just stare at the plume and guess what's inside, right? The sheer threat of carbon monoxide demands absolute precision. We need a specialized, foolproof toolkit to track it down, pull it out of a super complex, hot, dirty mix of exhaust gases, and measure it with total certainty. So here's our quick roadmap for this explainer. First, the carbon monoxide problem. Second, what is Method 10? Third, the equipment setup. Fourth, dealing with interferences. And finally, the final calculation.
Okay, moving right along to parts 1 and 2, the core problem and what Method 10 actually is.
At its core, Method 10 is the EPA-approved procedure for measuring carbon monoxide in stationary source emissions using a continuous instrumental analyzer. Now, what really makes this method crucial isn't just the fact that it measures the gas. It's the strict quality assurance and quality control rules built directly into it. If you're the tester out in the field, you literally have to document your adherence to every single requirement. You have to guarantee that your data is of known, verifiable quality. Regulators rely heavily on this exact method to determine compliance with strict federal and state air quality standards. And it's even used to test the continuous monitoring systems running 24/7 at these industrial facilities.
So, our precise chemical target is, of course, carbon monoxide, CAS number 630-08-0. But the absolute standout detail is the sensitivity requirement. The method demands an incredible sensitivity of typically less than 2% of the calibration span. Just think about that for a second. We're hunting for trace amounts of an invisible gas inside a roaring exhaust stack. The margin for error? Practically zero. The instruments have to be extraordinarily sensitive to pick out that specific carbon monoxide signal from all the background noise.
Now, to actually grab this gas from the stack, testers generally choose between two main approaches. First up is continuous sampling, where the effluent gas is sampled and fed directly and continuously to the analyzer. If you're familiar with Method 7E, you'll recognize this setup because it borrows a lot of inspiration and equipment specs from it. But there's a really cool operational part here. If you're transporting dry gases or measuring on a dry basis, you don't even need a heated sample line. That saves a ton of hassle out in the field. The second approach is integrated sampling. Here, instead of a direct feed, you're slowly collecting the sample over a period of time, using flexible bags or rigid tanks, which you then analyze later. Which brings us to Section 3, the equipment setup. Now, what's really interesting about this next part is our toolkit. If you're heading out to do integrated sampling, your gear list is super specific. It's essentially an unboxing of pure precision engineering. First, you need an air-cooled condenser to pull any excess moisture out of the gas stream before it wrecks your sample. Then, a precise needle valve to dial in your exact flow rate and a leak-free diaphragm pump to pull the gas safely through the system. You'll measure that flow with a rotometer capable of reading 0 to 1.0 liters per minute. But the absolute star of the show? The Tedlar flexible bag. The method calls for a massive capacity of 60 to 90 liters. It's basically a giant, heavy-duty scientific balloon. And you can't just trust it out of the box. You have to leak test this bag in the lab before you ever step foot on site, evacuating it completely and making sure that meter reads absolute zero flow. Here's how all that gear actually comes together. The stack gas enters through the filtered probe. It's drawn down into the air-cooled condenser. That's the box dropping out the moisture. The dry gas flows up, past the needle valve, through the rotometer, and is finally pushed by the pump into our giant flexible bag housed safely inside a rigid container. Honestly, for an even better understanding of what this looks like in the real world, you might want to pull up some Google images of Method 10 or look for pictures of a park lab station while testing is being performed. It really brings this whole schematic to life. And hey, quick favor, if you're finding this technical breakdown helpful and want more content where we turn complex source material into clear concepts, hit that like button and subscribe to the explainer. It seriously helps us out a ton.
All right, once you're on site, the operation follows a really strict sequence. Step 1, completely evacuate that flexible bag or tank. It needs to be totally empty. Step 2, set up your disconnected equipment just like the schematic we just looked at. Step 3 is absolutely critical. Place the probe in the stack and purge your sampling line. You got to flush out any ambient air so you're only capturing true stuck emissions. Step 4, connect the bag,
double-checking for an absolutely leak-free seal. And finally, step 5, start sampling at a rate proportional to the stack velocity. It is a highly orchestrated operation from start to finish.
Moving on to section 4. So the crucial point is that carbon monoxide isn't the only gas in the stack. We have to deal with interferences.
Method 10 explicitly warns testers about a very specific, invisible roadblock. The text states, substances having a strong absorption of infrared energy may interfere to some extent in some analyzers. So what does that actually mean? Basically, our primary continuous analyzers rely on infrared energy to literally see the carbon monoxide. But if other gases in the stack, especially carbon dioxide, which is everywhere in combustion exhaust, absorb that same infrared energy, they can trick the analyzer. The machine gets blinded, misinterprets the CO2 as CO, and spits out an artificially inflated, inaccurate reading. Definitely not good.
To fix this, Method 10 gives field testers two main options. Option 1 is digital, instrumental correction. This is where the analyzer itself is smart enough to digitally compensate for the interference of those other gases. Option 2 is physical, utilizing traps. Testers can use silica gel and ascarite traps to scrub the sample gas. The silica gel handles the moisture, while the ascarite chemically reacts with and physically yanks the interfering carbon dioxide right out of the gas stream before it even reaches the analyzer. And this brilliantly illustrates why we need one final purification step on paper. Section 5, the final calculation. Because here's the catch. If you chose to physically remove that interfering carbon dioxide using an ascarite trap, you fundamentally altered the overall volume of your collected gas sample. You shrank the total pie, and that artificially concentrated the remaining carbon monoxide. If you just trust the raw analyzer output, your number is going to be way too high. So testers have to mathematically correct it using equation 10-1. C average equals C CO stack multiplied by 1 minus F CO2. Let's translate that math into plain English. C CO stack is your raw, unadjusted carbon monoxide concentration, the number the machine spits out. F CO2 is the volume fraction of the carbon dioxide you physically removed in your trap. By subtracting that removed CO2 fraction from 1 and then multiplying it by a raw concentration, you adjust the scale back to reality. You get C average, your final, pristine average gas concentration. It's this beautiful piece of mathematical accounting ensuring the trap doesn't accidentally inflate the very numbers you're trying to measure. Which brings us to the end of the protocol. Method 10 gives regulators and scientists the exact tools, the rigorous equipment standards, and the flawless math to track down an invisible, highly toxic gas with incredible, repeatable precision. It ensures regulatory compliance, and it forces industrial accountability. But gathering perfect numbers, that's really just step 1. The real provocative question we have to ask ourselves is, now that we have this incredibly precise emission data, what policy actions will we take with it to actually protect our air and our communities? Thank you so much for joining me on this explainer. Keep asking the right questions, and I'll see you on the next one.